Imagine a study group where one student ranks first in the school in every single subject. Why would that top-ranked student ever spend time partnering with someone ranked 50th? The intuitive answer is that they wouldn't. To see why that intuition is wrong, we can look at a classic economic model featuring two people, Kwang-jae, a farmer who grows potatoes, and Ju-hae, a rancher who produces meat. This table shows their daily production capabilities. Looking closely, Ju-hae is objectively faster and better at making both items. She can produce an ounce of meat in 20 minutes compared to Kwang-jae's 60, and an ounce of potatoes in 10 minutes compared to his 15. When reading data like this on an exam, pay strict attention to the column headers. The left side measures the time required to produce a single unit, where lower numbers are better. The right side measures the total output possible in an 8-hour workday, where higher numbers are better. Ju-hae holds an absolute advantage across the board, yet the mathematics of economics dictate that she still needs Kwang-jae's help to maximize her own wealth. These two graphs map out a self-sufficient world where Kwang-jae and Ju-hae operate entirely alone, only consuming what they can physically make. These downward-sloping lines are their production possibility frontiers. You'll notice these frontiers are perfectly straight, unlike the bowed curves seen in other models. A straight line indicates a constant opportunity cost. Every time Kwang-jae switches an hour from potatoes to meat, he gives up the exact same amount of yield, regardless of how much he has already produced. If they divide their 8-hour days equally down the middle, Kwang-jae lands at point A, yielding 16 ounces of potatoes and 4 of meat. Ju-hae lands at point B, with 24 potatoes and 12 meat. In a self-sufficient system, a person's production possibility curve is identical to their consumption possibility curve. They are trapped by their own physical limits. Ju-hae proposes a strategic deal. She tells Kwang-jae to stop making meat entirely and specialize exclusively in potatoes. In return, she promises to trade him 5 ounces of her meat for 15 ounces of his potatoes. Pause the video here. Calculate Kwang-jae's final consumption based on these specific trade terms. Does this deal leave him better off than his self-sufficient point A? This summary table walks through the exact math. By specializing, Kwang-jae produces 32 ounces of potatoes and 0 meat. He hands over 15 potatoes and receives 5 meat in return. His final pile is 17 potatoes and 5 meat. Compared to his self-sufficient state of 16 and 4, this trade nets Kwang-jae exactly 1 extra potato and 1 extra piece of meat. Now look at Ju-hae. To fulfill her end of the deal, she spends 6 hours making 18 ounces of meat and 2 hours growing 12 ounces of potatoes. She trades away 5 meat, receives 15 potatoes, and finishes her day with 13 meat and 27 potatoes. Her self-sufficient baseline was 12 meat and 24 potatoes. The trade leaves her with a net gain of 1 extra meat and 3 extra potatoes. Both individuals, acting purely in their own self-interest, executed a trade that resulted in acquiring more goods than their maximum 8-hour solo capacity allowed. Let's plot these final mathematical results back onto our original graphs to see the visual impact of the trade. Notice the physical location of the new consumption points, A star and B star. They exist completely outside the original boundaries of the production possibility frontiers. Trade successfully separates consumption possibilities from production possibilities. It allows individuals and entire societies to consume far beyond what they can physically make. For your exams, remember these 3 rules. First, without trade, the production frontier equals the consumption frontier. Second, straight frontier lines mean a constant opportunity cost. Third, free trade pushes consumption outside the frontier. In the next lesson, we will closely look at the mathematical engine driving this result, the principle of comparative